This particular problem is focused on doing a calculation on cesium chloride, where we've been asked to compute the theoretical density of this particular ionic solid. And so from the diagram of the crystal structure of cesium chloride, what we see is that there are chloride ions at each of the corners of the unit cell, and just kind of putting a little hatch on them right now. So in terms of numbers of chloride atoms per unit cell, we see that there would be 8 chloride atoms times 1/8 per corner site, which would equal 1 chloride ion per unit cell. And then similarly, it's kind of easier to instantly recognize that the number of cesium ions per unit cell, we can say by inspection, is 1, because we can see that 1 in the body center. And this makes sense to us because the ionic compound is cesium chloride, and so we do expect there to be a 1-to-1 correlation of number of ions in the unit cell. So the other thing I want to point out from this diagram is that when we think about the packing of ionic solids, and cesium chloride is an ionic solid, we must think about where the atoms are physically touching. Notice that the chloride ions, the ions at the corner, do not touch each other along the edge length or the lattice parameter, and so that's kind of particularly evident, I think, on this part that I'm just notating here. You can see that there's clearly a gap. And so that's not useful to us right now in terms of figuring out what the lattice parameter A is. And remember, A is just the edge length of the unit cell, of the cubic unit cell. What is more evident to us when we look at the kind of three-dimensional large volume ion depiction is that touching of the atoms is going to be occurring on the body diagonal. So let me just kind of draw this with tiny crosshatches here. And then it's a little more easy to see in the point lattice diagram on the left, where the atoms are not drawn to actual size. And so while we're looking at this, I know in advance that we're going to want an expression for the lattice parameter A as a function of these various two radii, the radius of the chloride ion and the radius of the cesium ion. And so by inspection, we can see that the body diagonal is, its length will be equal to 2 times the radius of the corner ion, which in this diagram is chloride ion. So I'll write R radius of chloride ion plus 2 times the radius of the cesium ion. And I've just given one the symbol little r and the other symbol capital R arbitrarily. And so the length of the body diagonal is just that's the R here plus another R for that, and then the same R again, and then the fourth R. So in other words, relative to this colored diagram, it's 1 purple radius plus 2 green radii plus 1 purple radius. All right, and so mathematically, we appreciate from the Pythagorean theorem and doing some geometry that this length of the body diagonal is also equal to the square root of 3 times the lattice parameter. Or another way of saying this is that the lattice parameter is equal to 2 times that little radius plus 2 times the bigger radius, whichever one is bigger, it doesn't matter, divided by a square root of 3. All right, so the key point here is that you need to notice where atoms touch. And then use that relationship of the touching radii to come up with an expression for the lattice parameter A. So let's kind of go back to what we're trying to find. So theoretical density. Density has units of grams per centimeter cubed. So we are trying to figure out how many grams in a cubic centimeter. And the volume that we've just been considering is the volume in a unit cell. So the way I'd like to begin this is by thinking about how many grams of those atoms are in that unit cell, and then to convert my way into centimeter cubed by just, doing dimensional analysis. So we want grams in the numerator. In the denominator, what I can see is that we're going to want A cubed, right? We're going to have that, and then we're going to do some conversions, and we'll do that part later. But I kind of want to focus on the numerator. And so in order to get grams, we need to think of something that has grams in it. And the only thing that really has grams in it that comes to mind from what we've been learning so far is the atomic mass of those two ions. And so cesium has an atomic mass of 132.91 grams per mole, and chloride ion has an atomic mass of 35.45 grams per mole. And there's one atom of cesium inside that unit cell and one atom of chloride in the unit cell. So the mass inside the unit cell is going to equal 1. Let's do chloride first. So 1 chloride ion times 35.45 grams per mole times a mole for 6.02 times 10 to the 23rd atoms, and actually it's 6.022 atoms. And so let's kind of write this first part as 1 atom. All right, and so now we can see that the atoms cancel out, the moles cancel out, and we're left with grams. So this would be how many grams of chloride ion. So this part was about chloride. And then we need to kind of figure out how many grams of cesium there would be. So again, there's 1 cesium atom times 132.91 grams per mole of cesium. And I put Avogadro's number in this configuration because we need it to be canceling out the moles. And so this will give us the total mass inside one unit cell. And so, in other words, the mass in 1 nanometer cubed, or not 1 nanometer, the mass in an A cubed is going to equal all that divided by A cubed. So, and let's go ahead and substitute A in for what we had already solved it to be, which would be 2r plus 2r over square root of 3. And actually, let me solve for that quickly up here. So 2 times little r, it would be, let's see, 0.181 plus 2 times 0.170 over the square root of 3. And if you do that calculation, you get that A is equal to 0.4053 nanometers. Okay, so if we plug in that number down here and carry it all through, what we get is 4.1992 times 10 to the minus 21 grams per nanometer cubed, because A is in nanometers. All right, we're getting closer. Now we just got to convert into grams per centimeter cubed. So I'm going to just kind of do some conversions here. So that's going to equal 4.1992 times 10 to the minus 21 grams per nanometer cubed. And I'm going to multiply by 1 meter for every 10 to the 9 nanometers. We have to cube that whole thing. And then I note that in every meter, there are 10 to the 2 centimeters. And that would need to be also cubed. Okay, and so In this denominator, I'm going to just do some out loud math. We have, it'll be 10 to the 6th divided by 10 to the 27th, and so that would be equal to 10 to the minus 21. So all of this corresponds to equaling 10 to the minus 21, and so therefore, and you plug this in your calculator if you prefer. So therefore our answer, and I'm going to round up a little bit, is going to equal 4.20 grams per centimeter cubed. So that's our final answer. And I want to kind of harken back to the problem statement. So notice that it tells us that it has a measured density of 3.99. And so because we're close, right, because it's close to 3.99, I find this answer believable. If I had an answer like 8.4, I would say to myself, no, something's wrong here. But and the problem statement kind of gives us a warning. It's telling us, it's not going to, the theoretical density won't exactly match the measured density, and here's why. Quote unquote, this slight discrepancy is due to the coordination numbers of cesium and chloride ion. Typically, ionic radii are listed for coordination number of 6. All right, so this wraps it up. This is the final answer for this problem. And if you have any, this particular, I'm just going to highlight a few things. So this number of one atom, kind of up here that I'm making green, one chloride ion, right? That's because there's one, chloride ion in the molecule, right, and one in the unit cell. And let's make this orange now. The one cesium ion, right, it's because there was one cesium ion in the unit cell. Sometimes unit cells will have different numbers than one. So those highlighted areas in this equation would be where you take that into account. All right, that's it.